Welcome you in the lecture series of Basics of Communication Engineering. It is 18th lecture of this series. In previous lectures, we have discussed about continuous wave modulation such as amplitude modulation, frequency modulation and phase modulation, where the carrier was continuous sine wave. From this lecture, we will discuss about pulse modulation, where the periodic sequence of rectangular pulses is used as a carrier wave. In this lecture, I would like to discuss about sampling theorem, and the outline of this lecture are Introduction, Low Pass Sampling Theorem, Reconstruction of Original Signal, and Sampling Theorem, where we will discuss ideal sampling, natural sampling, and flat top sampling. And in the objective of this lecture, you will able to explain why the need of sampling and different types of sampling techniques and how can you reconstruct the original signal from the sampled signal. Different types of modulation techniques are there. In all the continuous wave modulation like amplitude modulation, frequency modulation, phase modulation, information about message signal is transmitted continuously in terms of corresponding variations of amplitude, frequency or phase of the carrier wave as the case may be. If the message is band limited, low pass, then sampling theorem says that it is not necessary to transmit the information about the message signal continuously. It is enough if we transmit its samples, since the receiver can reconstruct the message from these samples. There are different methods that one can adopt for representing the sampling values and transmit them to the receiver. In this technique, a periodic sequence of rectangular pulses is used as a carrier wave and give rise to different pulse modulation scheme like pulse amplitude modulation PAM, pulse width modulation, or you can say pulse duration modulation, and pulse position modulation PPM. And these techniques are known as pulse analog modulation, whereas the pulse code modulation and delta modulation and adaptive delta modulation, these modulation techniques are known as pulse digital modulation. Now, the sampling is the process of converting a continuous analog signal to a discrete analog signal, and the sampled signal is the discrete time representation of the original analog signal. In transmission of discrete time analog signal, the average transmitted power is low, and with the discrete time analog signal, it is possible to have time division multiplexing of a transmission of several messages simultaneously over the same physical channel. But one disadvantage of this technique is that it requires large transmission bandwidth. So here this is the continuous time analog signal, and if we are doing sampling with the sampler, we will get discrete time analog signal. Here time is discrete, but the amplitude is still in analog form, and this type of transmission will require larger bandwidth. But here we can use TDM, time division multiplexing technique. Means if there are three users, one user can transmit their first sample, and the other user can also transmit their second sample, and third user can also transmit their third sample also simultaneously. So different user can assist the channel simultaneously. Now, low pass sampling theorem, in order to represent the original message signal faithfully without loss of information, it is necessary to take as many as samples of the original signal as possible. Higher the number of samples, closer is the representation. The number of samples depend on the sampling rate and the maximum frequency of the signal to be sampled. sampling theorem was introduced to the communication theory in 1949 by Shannon. So this theorem is known as Shannon's sampling theorem. Now the statement of low pass sampling theorem. Let xt is a band limited low pass signal and band limited to FM. This means the XF is 0 for all value mod F greater than equal to FM. This means if F having greater than or greater than FM, or here less than minus Fm, so we will have the XF, it will be 0, and in this it is band limited from minus Fm to plus Fm. Then it can be completely represented in its sampled form and recover back the original signal from the sampled form if the sampling frequency Fs is 2 times the frequency of the signal, maximum frequency component of the signal, where Fm is the maximum frequency of the continuous time signal. So here the sampling rate Fs can be greater than equal to 2 Fm, or sampling period Ts1 by Fs, it will be less than equal to 1 by 2 Fm. If the sampling rate Fs is equal to the twice of the maximum frequency of the given signal 2 Fm, then this is known as Nyquist rate, and the reciprocal of the Nyquist rate is the Nyquist interval, and so the Nyquist interval, it is 1 by 2 Fm hertz. This is 1 by 2 Fm second, and Nyquist rate Fs is 2 Fm hertz. The sampling theorem is also known as Nyquist theorem. Here you can see this is continuous time analog signal xt, and if we take the samples instead of this continuous amplitude, if we take some uh, samples of for this signal at a different instant of time, and if we are using unit impulse train as a sampling function or carrier wave, or you can say here st, it can be represented as del t minus impulse train. So here we will get our sampled signal at this instant. So we will get the impulses at this instant. This impulse, amplitude varying impulse, are the sampled signal, and this sampled signal is denoted as x del t, and the duration here between each impulse train, it is ts. Let us represent the instantaneous amplitude of xt at various sample point t is equal to nts. So the amplitude at this instant is represented by a circle here. These are represented in this equation by a circle, these amplitudes. And this x del t, it can be equal to xt into st the train of impulse, or in any instant the amplitude of xt can be represented as t is equal to nts into xt. Here st is summation minus n minus infinity to infinity delta t minus nts, and this is uh, train of impulses. Now the mathematical expression for the sampled signal x del t, it can be given as summation minus infinity to infinity x nts, and st is here delta t minus nts. And so if I will take the Fourier transform of this, then this impulse train, so sf, it will be fs summation minus infinity to infinity delta f minus nfs. And also the Fourier transform of this sampled signal in equation first, it can be represented as delta x delta f, it is xf, and convolution sf, xf and sf. So this is because the Fourier transform of the product of two signal in time domain is the convolution of their Fourier transformation. So from this equation third, we can have x del f, it will be xf convolution sf. So from this equation we can have xf convolution sf summation minus infinity to infinity delta f minus nfs. And here this is the convolution, and interchanging the order of convolution and summation, and we can have by interchanging these orders x delta f, it is fs summation minus infinity to infinity xf convolution delta f minus nfs. From the property of delta function, the convolution of xf and delta f minus nfs, it will be, the property of delta function xf convolution delta f minus nfs. So it will be xf minus nfs. So we can have the sample signal x delta f, it will be fs summation minus infinity to infinity x f minus nfs, where xf is the Fourier transform of original signal xt, and the term xf minus nfs in this equation 8 represents the shifted version of the spectrum xf of the original signal xt. So depending on the value of n, we will get infinite number of original spectrum xf centered at the frequencies 0 plus minus fs plus minus 2fs and so on. So we can represent xf minus nfs. It will be fs at frequency 0 plus minus fs plus minus 2fs plus minus 3fs plus minus 4fs and so on. So the sampled signal x delta f, it will be fs summation minus infinity to infinity x f minus nfs. So we can write it will be equal to uh, dot 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 plus fs x f plus 2fs plus fs x plus fs plus x fs xf plus fs x minus fs plus so on. So here the first term is the xf shifted left by 2fs. So the spectrum of xt is shifted to left by 2fs, and the spectrum of spectrum of xt is shifted left by fs in the second term, and this is the spectrum of xf, and here this is the spectrum of xf it is shifted right by fs. So the minus indicates shifted to right and plus indicates shifted to left. So the spectrum of a sampled signal, it can be represented if the spectrum of the baseband signal xt is given by this xf from minus fm to plus fm, then the spectrum of the sampled signal, it will be the first term, the spectrum of xf is shifted left by 2fs, and second term the spectrum is shifted by fs, and the spectrum, this is the spectrum of xf, and this is the fourth term, spectrum is shifted right by fs, spectrum is shifted right by 2fs and so on. So this is the spectrum of the sampled signal. Here if the signal xt is not strictly band limited, so we have considered that the signal is band limited minus fm to fm. Now the case when the signal is not strictly band limited, and or if the sampling frequency fs is less than 2fm, basically fs should be greater than equal to 2fm. If fs is less than 2fm or equal to 2 or less than 2fm, then an error is occurred, and this error, it will be aliasing or fold over error, and it is observed in the spectrum. And this is the spectrum, overlapping spectrum, and here you can see the higher frequencies in xt take on the identity of the lower frequencies due to aliasing. So this is the higher frequency component, and but it will take the identity of lower frequency component, and this is known as the aliasing or fold over error. So in this case, this phenomena of high frequency in the spectrum of the original signal xt takes on the identity of the lower frequency in the spectrum of the sampled signal x delta t is known as aliasing or fold over error. Due to aliasing, some of the information contained in the original signal xt is lost in the process of sampling. So now, how to recover the original signal or reconstruction of the original signal? When the sampled signal x delta t is applied to the input of ideal low pass filter or reconstruction filter, this filter allows only the shaded portion. So if this is your spectrum of the sampled signal, and this is the frequency response of the low pass filter, and this is the shaded spectrum. So this filter will allow only the shaded portion in the spectrum of the sampled signal to pass through the output as in figure. So from the low pass filter, only this portion will be passed out, and will block all other frequency components. So the frequency components only corresponding to xt will be output of the original signal, and xt is recovered back. So here we will recover the spectrum of the our original or message signal. This is the idea behind the reconstruction of the original signal. Now the question is still how to eliminate the aliasing if the fs is less than 2 fm, and or you can say the signal is not band limiting. The aliasing can be prevented by using an anti-aliasing or pre-aliasing filter and using frequency fs greater than 2 fm. So first point, if the signal is not band limited, use a band limiting low pass filter and pass the signal xt through it before sampling. So we will have the signal which is not band limited, then it will pass through the band limiting low pass filter. Now your signal is strictly band limited. Now we can do the sampling, and we can eliminate the aliasing in the sampling. This filter has a cutoff frequency fc is equal to fm. So it will strictly band limit the signal xt before sampling take place, and this filter is also called as anti-aliasing filter or pre-aliasing filter. Now second point, to eliminate your aliasing, increase the sampling frequency fs to a great extent, means fs very greater than 2 fm. Due to this, even though xt is not strictly band limited, the spectrum will not overlap. A guard band is created between the adjacent spectrums. Just like if fs is very greater than 2 fm, then there will be guard band, because we have considered one spectrum, then another spectrum is there, but fs is very greater than 2 fm. So there will be space in two spectrum, and this is guard band is created between the adjacent spectrums. So now it is possible to use practical low pass filter without introducing any distortion due to the presence of a guard band between the adjacent frequency spectrum. So if we use the practical low pass filter, so the practical low pass filter, this is the response of the practical low pass filter. It is not just like this is ideal filter, but the practical filter having the response like this. So we can reconstruct our original signal using this practical low pass filter if fs is very greater than 2 fm. So now the sampling techniques. Basically there are three types of sampling techniques: ideal or instantaneous or impulse sampling, natural sampling, and flat top sampling. The sampling technique which we have discussed here in this lecture, which uses unit impulse train as a sampling function, is known as ideal or instantaneous or impulse sampling. The natural sampling In the natural sampling, the duration of the sampling pulses is finite, is of finite duration, and amplitude of the pulse is also finite, and it uses chopping principle. And the flat top sampling can be obtained using sample and hold circuit, and we will discuss about these sampling techniques in detail in the next lecture. We have already discussed this ideal sampling in this lecture, and we will discuss about these two in detail in the next lecture. And this is the end of this lecture. Here we have discussed about sampling theorem, aliasing, and types of sampling technique. This was 18th lecture of the lecture series of Basics of Communication Engineering. In the next lecture, we will discuss about different types of sampling techniques in detail. Till then, thanks for listening this lecture. Thank you.